have an enormous impact on probabilities because it's going to involve putting together exponentially small numbers, which of course vary from each other by exponential amounts. You might have one by 10 of each of the 1 million and another of each of the 100,000, and those are very different. So how do we construct a probability measure? There's actually only one pitfall, I think, and otherwise it's fairly straightforward. What we know, at least in the landscape, in the terminal landscape that I consider for the example, is that our world line is going to end up in Z sooner or later, and that's where it ends. Okay, so with the probability goes to 1 at late times, you're going to end up in Z for the same reason that with the probability that goes to 1, the radioactive atom is eventually going to decay. Okay, and so the first guess, which is not a very good guess, of how to define probabilities for the world line, is to say, well, let me define the probability for vacuum I to be proportional to the expected amount of time that the world line is going to spend in vacuum I on its way down into Z. And the reason why that's not a very good guess, and this is a really important point, I think, is that the lifetimes in a landscape with longest metastable vacuum are typically exponentially long. And in fact, they're exponentially longer than the thermalization time scale for vacuum. Think of our own vacuum. Our own vacuum might live for some exponentially longer time than 10 billion years. Okay, that time is completely dead time. It doesn't buy our vacuum anything in terms of being more frequently observed. Okay, it doesn't mean that it's just going to be empty to space. There's nothing there. So there's a subtlety that I've been agonizing about, which is that you don't want your vacuum to be too stable either, because at some point you get into the Boltzmann-Strain paradox, and it becomes more likely to create observers by bizarre random fluctuations than in the honest old-fashioned way. And but I'd like it's possible. I mean, this is a very interesting discussion, but it's going to go completely off. So I'd like to stay on track and maybe have that discussion at the end of the talk. Okay. I mean, I think it's a very interesting question, but it's sort of orthogonal. And in my view, it's a constraint. It's a consistency condition on the string theory landscape. You want that to be stable enough, but not too stable. Okay, so the main model that I want to get out of here is that we don't want to make the mistake of rewarding a vacuum for sitting around doing nothing for some exponentially long amount of time. Okay, and these factors are huge. So as a zero-order approximation, I want to do better than that. And what we're seeing, of course, in our own vacuum is that even if it lives for an insanely longer time, like it's a subtlety, everything interesting happens at the beginning. Okay, everything interesting happens when the bubble is nucleated between that time and the time when everything's thermalized and the state is emptying out. It's the out of equilibrium period that's the most interesting period. Okay, that's when complex structures can form. That's when presumably observers arise. And I'll get back to that point when it comes to the question of weighting vacuum in more detail. As a zero-order approximation, what I want to take away from this is that the most important thing is to just get into your vacuum. It's just producing it. Of course, you don't want it to decay very, very fast. But compared to the exponentially long time scales we're usually talking about, the good first approximation is just being interested in the expected number of times the world line is going to enter a given vacuum. That's when there's a potential for something interesting happening. Okay, so that's what I'm going to compute. And in order to compute that, it turns out that you don't need all of the information that's contained in this matrix kappa, because you don't really care how long you think you'll live. When you're in A, you're only interested in where am I going to go next, not when am I going to do this. So what's the relative probability to decay into B or C or D? And the relative probability I can compute by dividing out by the probabilities to decay at all, which is the probability from A to all the different J's it can go to. And so I get a matrix that is contains less information in the sense that it guarantees that all of the columns here sum to 1 except for the terminal vacuum, which is still 0, and which you don't normalize in the same way. Okay, so here's a vacuum A that has to go to B. Remember the drawing. B can go back up to A or down to Z, and there's one free parameter here. It has to add to 1. It has to decay at some point. And Z doesn't go anywhere.